I will try to convey our experience during the last 17 years trying to use electrical impedance tomographs in ICU environment. This talk will be very, very applied, and I hope this can be useful for fine mathematicians. I will talk of the design of electrical impedance tomographs using the observability concept, a very simple concept from the control theory. First, an introduction of the medical problem. Then I will explain how we regularize our problem. Then I will address the control theory, how we can use the control theory to design tomographs. And finally, we will try to show some numerical simulations showing that this concept is very useful. The medical problem that we address is the problem of the patients that are in the ICU environment. And normally they have a pneumonia caused by very different reasons. Here we have in the left an X-ray showing some changes in the right lung, and the CT scan slice in the right figure. This figure was given to me with permission to show by Marcelo Amato. There was, in the beginning of the pneumonia caused by the virus H1N1, all the patients were showing some strange modifications in the lung tissue, and there was no medical protocol to treat this, and 100% of the patients at that time went to obit. They died. In this moment, EIT, medical doctors were using EIT to develop a protocol. And this protocol has two columns. The column in the left shows in white the regions of the lung that we estimate that are over-distended. When the lung tissue is over-distended, if you drop the pressure, the lower pressure, the resistivity changes very little. So from one line to the other line in those graphs, we are dropping the pressure from 23 centimeters of water to 21, from 21 to 19, 17, 15, and so on. In the column, the right column, we estimate the regions of the lung that are collapsed. We know the regions that are collapsed because the variability, the variation of the resistivity is caused by perfusion of blood and not by ventilation. And so, the protocol was to avoid the white regions because they have no ventilation, no practical perfusion, because the walls of the alveoli are so stressed that the red cells cannot move through the alveoli. And we need to avoid also the blue regions, because in these regions there is no ventilation at all. The lung is collapsed, and worse than that, around these regions there is an hemorrhage, and the patient is bleeding in this condition. And so doctors, they decided to keep the PEEP, the lowest pressure at the end of expiration, in this level where there is minimal atelectacy, collapse of the lung, and minimal overdistension. And this protocol saved many, many lives at that time. And here is this patient 3 days later with a much cleaner lung. In the 90s, Brian Brown and a collaborator called Knopp, they developed a model of the walls of the alveoli, and experimentally and theoretically, they said that the variation of impedance of the lung tissue is linear with the variation of gas inside the lung tissue. But at that time, they used volunteers to make this the experiments, and so they had a small part of the range of gas content in the lung tissue. 2 years ago, those experiments were repeated, but this time from total collapse to pneumothorax, and so in a very large range of gas content. And it was done in an experiment with 7 pigs, and the gas content was computed using a CT scan. And this linearity between the impedance and the gas content is the reason why this technique is being well accepted by doctors. And so we can estimate the gas content through the change of impedance in the lung tissue. Nowadays, the technology that is in the market, it's gives only images of variations of resistivity. But for many reasons, and some pathologies are not visible in those images, and so we need absolute images of resistivity and not variation of resistivity. So a pneumothorax is not visible, an hematothorax is not visible. The accumulation of fluids, the nature of the fluids that are being accumulated is not visible nowadays, especially the presence of the absence of blood in the fluids. And so around 2005, we made an agreement with Jari Kaipyu. At that time, he was working at the University of Kuopio. Now I think the name is Eastern Finland University. And he suggested us to regularize the problem using anatomical and physiological data. And the idea was to use Bayes' theorem and to admit a prior probability density function that was Gaussian. So the idea of this theorem is very simple. We can compute easily the voltage in the boundary of a domain, knowing the current and knowing the resistivity. And the theorem says that the probability of a certain distribution of resistivity, knowing the voltage in the skin, is proportional to this product. This is called the likelihood, and this is called the prior information. And so we face the challenge of how to estimate the prior distribution of resistivity inside the thorax, and we decided to begin using pigs, the thorax of pigs. We decided to develop 5 different anatomical atlases, or a priori distribution of resistivity of 5 different slices, because the pig has a very different anatomy depending on the distance from the cranial-caudal distance. And so we used 360 CT scans. We segmented all of those images, and we computed in this model. To build this model, we need basically a vector, this vector, rho bar, that is the expected resistivity distribution in the lung, in the thorax. And we need also this gamma matrix that is the covariance of all of these samples. And so we segmented all of those images, and we found a common domain. We enforced that all the rib cages had the same height and the same width, and we found a common domain. After the segmentation, we had for each image at that moment 5 different tissues, and the tissues were bones, muscles, lungs, air. Nowadays, we work with 8 different tissues. And so the anatomy, we had it statistically through the CT scans. But our model was based on resistivity, and so there was no other way but measuring directly the impeditivity of the tissues of the thorax in vivo. So 9 pigs were tested. The experiments, the data collection took now 9 hours each pig. And we used, so we needed to extract the sternum. And we used a probe to measure the impeditivity of all the tissues. Typically, in the left top graph, we have the real part of the impedance, and we have some large variations that are due to the breathing, and some smaller variations that are due to the blood perfusion in the lung tissue. And so with measurements like this, directional measurements like this, because in the muscles we need to measure along the fibers and across the fibers. There is some anisotropy. And at the end, the rho bar vector is depicted here in this slide. We have five slices, and this is pretty much the rho bar that's part of our statistical prior information. We were surprised how beneficial was to use this statistical regularization. In our minds, whenever we use the statistical regularizations instead of Laplacians or other mathematical functions, we get an increase of 3 times in the resolution. The resolution gets 3 times better. And so, one thing that's difficult to capture in the lung is the perfusion of blood. It's a lot more difficult to capture the perfusion of blood than ventilation. And here in the left, we have a Laplacian regularization. In the middle, we have the use of the expected resistivity of a population of pigs. And in the right, we are using the expected resistivity and the covariance and Bayes theorem. So and this is how the blood leaves the heart on top and goes to the lungs, down, and then go back. And we can see a Y letter here showing the separation of the tissues. And we were happy with this, but we were certain that this was wrong. And this is wrong because all of this was done with a belt of electrodes in a single plane. And now I want to show why this is wrong, this is biased. Although it's a nice movie of the perfusion, why this is biased. And so I will recall the simple equations of control theory of linear invariant systems, equation 3 and equation 4. A has all the evolution information in time. B has all the information of the excitation. In our case, this is current. C has all the information of electrode placement and the measurements, and which localizations in the skin are being measured. Since we work in the discrete time field, we need to integrate that equation 3, and we get equation 5. And during this integration procedure, there is a relationship between the evolution matrix A like in equation 6. Now we do, for our design objective, we use the hypothesis that A, it's almost null. And with this hypothesis, that's a nice hypothesis because we capture the data in 100 times faster than the heart beating. That is the faster phenomenon that we want to observe. We perceive that G becomes the identity matrix. And running this equation 5 a couple of times under null initial conditions and relating the state with the history of excitation U, we find a matrix that's called the controllability matrix. And this controllability matrix has several times and powers of G. But G, for our purposes, is the identity. And there is no need to continue in this sequence because of this Cayley-Hamilton theorem that states that there is no more information in the next column here. And so, if n is equal to and G is the identity matrix, the observability matrix in this example gets only this, and G is the identity matrix, and the rank of the controllability matrix is exactly the rank of H. And H is easy to be computed. In the same way, we can, running equation 5, under the hypothesis that excitation is null, we can relate the observations with the state, and in that situation, the history of observations and the state will be related by a matrix called the observability matrix that has also powers of G. But G is identity, and the rank of the observability matrix is precisely the rank of C. C and H matrices are the ones that we compute by finite elements. And so we can see here the equation of finite elements. X is the electric potential in the finite element mesh, and U is the excitation, is the current excitation, and Y is the conductivity matrix. The inverse of Y creates a relationship between electrical potential, or the state, and U, the excitation in current. And all of this is called the H matrix. So H matrix is easy for us, and we have just perceived that H matrix can be used as controllability matrix. And so H matrix, we will use H matrix as the controllability matrix. It has all the information of the electrode positioning, the boundary geometrical information, and the impeditivity distribution. At the same time, C can be used as an observability matrix, and under initial conditions, null initial conditions, we have equations 14. And especially we can write a relationship between measurements and the excitation that will be observability matrix times controllability matrix. So this is what is stated here. And we know how to compute these three matrices. T is just a matrix that says in which electrodes we are injecting current. And so the transconductivity matrix can be explained by observability times controllability, and this transconductivity matrix can also be seen as a singular value decomposition, and we can build it's interesting to build a observability matrix that is U times the square root of sigma. Sigma is a diagonal matrix. And in this situation, the singular values will, the small singular values here will filter out which states cannot be measured. So the singular values, all the singular values that are very small will make the columns of U disappear from the measurements. And so we can use the small singular values as observability indexes, directional observability indexes. We know the directions that we cannot measure because the singular values are small. At the same time, we can see at the same time a controllability matrix that is the square root of sigma times matrix V transposed. And in this case, the singular values indicate which directions of the excitation space will not excite the domain. See, this is a vector times a diagonal matrix, and if the diagonal is very small, the excitation will not contribute to the state. And so we can use the singular values in this internally balanced model as controllability and observability directional indexes. And so now I will show some numerical simulations showing that we need to respect the singular values of the conductivity matrix because, for instance, if we have all the electrodes in a single plane, as all the current technology in the world does, everybody does this in the world, and we have an object moving from the equator to the North Pole, if we have all the electrodes in a single plane, we will observe two objects instead of one. We lost observability of the anti-symmetric modes. If we have two planes, even if they are very close to each other, then we recovered the information that we have only one object moving towards the North Pole. In a more realistic situation, if we use this rib cage and this lung tissue in a numerical phantom, in red you can see the bones, and so this is the sternum, and here the rib cage, and here the spinal column. If we use a planar disposition of the electrodes, the spinal cord gets totally, the bony region is perceived in the wrong situation. The inverse problem, using a non-planar belt of electrodes, we recover the sternum and we recover the spinal cord and some overinflation in the lung, and the heart position is in the correct position. And so, since many of the tomographs in the industry now use single-ended measurements and another use differential measurements, we will compare these two situations. We will form a matrix of measurements for each current pattern of excitation, and so we will form this matrix, and we will study the singular values of these matrices. all of them are easily computed. And if we want to study the differential measurements, then we have one more matrix here that captures measurements in a subtracted way. Here we can see the singular values. Each color represents a kind of excitation that skips some electrodes in the belt. And so we can skip one electrode, non-electrode 1, 2, 3, 4, 15. And if we are taking single-ended measurements, we will have this kind of singular values. And we are concerned with the smaller singular values. If the measurements are differential, then the smaller singular values are much smaller. And this is due to the fact that the differential measurement or the differential excitation matrix has the rank of this matrix in terms of the number of electrodes that we skip varies very much. And so the rank can be 15, the matrix is 32, the rank can be 24 in certain conditions. And so if we try to recover the image, skipping 6 electrodes, we have this image. Skipping 7, we have some artifacts. Skipping 14 is pretty much the same as skipping 6. And skipping 15, we will see an artifact and we will see 2 objects. And this is perfectly consistent with 15 and 7, 6 and 14. Let us try to make another experiment, a numerical experiment. We will try to, this is direct problem, this is the numerical phantom, and we want to find these red objects. So if we use 2 planes of electrodes, the objects are here, and there are some artifacts in the corners. If we use just 1 plane of electrodes, then there is a huge artifact here. In another slightly more realistic numerical phantom, we have a rib cage here, similar to the thorax, and we want to find these 2 objects. If we do a skip 2, this is pretty much the same image as the skip 4. But observe that skip 3 has a very large artifact here, and this is consistent with our singular values and the rank of matrix T and D. This can be used, this criteria of observing just the small singular values can be used also to design the shape of the electrodes. And so from the electronics, we know that the electrode must be large to diminish the electronic noise. And the gap between electrodes should be large to minimize the current shunt. The current shunt is the current that flows through the electrodes in the skin and does not help the inverse problem. And at the same time, we want to maximize the observability, maximizing the smaller singular values of the transconductance matrix. And so now we are trying to find the optimal shape of the electrodes in a zigzag belt, trying to minimize the shunt, trying to minimize the electronic noise, and trying to maximize the observability of the antisymmetric modes. And so we can imagine, we can make a plane, a diametral plane across this cylindrical phantom. And in this plane, I can integrate all the current that's crossing the vertical slice of this plane, the closer vertical slice of this plane. And I will see a picture like this one. And the first column here is the shunt current, and it's the one that we want to minimize. We can also integrate in horizontal slides the current that's crossing when I inject current from here and take off the current from here. And we will see this, and there is a center of current flow that the lower the center, the higher the observability of the anti-symmetric modes. So this is something that we are doing now. And so the conclusions are singular values of the transconductivity matrix. They define which directions of the measurement space will not be measured and which directions will not be observable, and the directions of the current pattern space that will not excite the domain. So image quality is related to the smaller singular values of the transconductivity matrix.
Thank you very much. Thank you.